저는 뭐 한국에서 초등학교, 중학교, 고등학교 다 나오고 회사에서 일도 해서 사실 한국말을 영어보다 더 잘하는 거는 당연 사실인데 제가 발표를 한국말로 해보려고 하니까 또 그건 또 쉽지 않더라고요. 그냥 발표 자료 같은 걸 다 영어로 준비해서 그래서 발표 자체는 영어로 할 건데 중간에 뭐 궁금하신 점이 있으면은 한국말이나 영어나 상관없이 그 채팅창에 올려주시면 제가 그때그때 답을 하고 중간에 이렇게 질문을 모아서 한번 정리할 수 있는 기회도 갖도록 하겠습니다. 네. 그래서 저 이름은 박태성이고 만나서 반갑습니다. 저기 보시면은 제 사진도 있고 제 와이프 사진도 있고 뭐 저희는 2년 전에 결혼했거든요. 그래서 결혼하고서 미국을 막 여행하면서 여기저기 로드트립도 가서 사진도 많이 찍고 그랬었어요. 그래서 코로나 바이러스 상황에서 나름 행복하게 보냈다고 할 수 있는데 여기서부터 영어로 해보자면 I'm a hobbyist photographer. So I like taking landscape photos. And here are some photos that I took. I'm just gonna show you some photos that I take. So this is Berkeley campus. And this is Bay Area in springtime. It's very pretty. And this was ICCV 2017 in Venice, Italy, when there was no pandemic. And I'm just saying and showing all these photos just because I just want to emphasize that when I take photos as my hobby, I like my photos to have vibrant colors. But of course, it's not always so easy. For example, this photo was taken last year during our road trip when there was a wildfire in California. And this wildfire made the back mountain look very hazy. But I put that photo on Photoshop anyways and play with contrast and color. There you go. It looks much more vibrant. But I still wish I can do more with it. So in Photoshop, you can maybe increase brightness and contrast, but you wouldn't be able to do bigger edits like changing time of day or maybe changing the season. And let me tell you why these edits are not possible with Photoshop. Well, it's because the output can only be generated using the pixels of the input image. But if you want to add snow to the input image, you must have seen that snow pixels from somewhere, and that somewhere is clearly not the input image. This is exactly where machine learning can come into play. We can gain generic visual knowledge about the visual objects from a data set, and we're gonna use that for creating new realistic visual that is nowhere present in the input image. So let's think about how to approach using machine learning for creating this type of new images. Well, I'm sure most people here will think about or heard about GANs. GANs work by randomly sampling a latent Z vector and transforming it to a realistic image. The realism is enforced by simultaneously training a discriminator network that determines if the generated image looks realistic or not. One interesting point about GANs is that they are actually like a random image generator. So if I want to edit my own face, I should first find the corresponding latent vector that's going to reproduce my face. But it's not an easy thing to do. So I can perform this test time optimization in the latent space so that the output actually matches my photo, but it's very slow and it's also imperfect. Here's another example of trying to reconstruct an outdoor image. The two buildings are totally different. And for the purpose of image editing, there's really no reason that the output images should be generated from randomly drawn numbers. So instead, my generator for image editing is gonna begin with the input image. Then from an external data set, I hope to learn some way to blend in the pixels of the input image with the visual knowledge that's extracted from the data set. Of course, this is not going to be an easy thing. So you're basically training a neural network on the training set, but at the test time, it should work well with the user-provided test image. So this is going to be a typical machine learning problem between training and testing, but it's not only that. So if you take too much from the data set, then you're ignoring the input image, and we're kind of back to this random image generation scheme of unconditional GANs. On the other hand, if you take too much from the input image, then you're not making meaningful edits to the input image. So there is an inherent conflict between the input and the data set. So for this scenario, our model needs to somehow disentangle the notion of snow from its geometry and apply it to the structure of the input image. So my works primarily focus on solving this conflict. What's the most straightforward way to learn this disentanglement? Well, we can have our model directly learn from examples of input and output pairs created with human annotation. It's surely going to be expensive to prepare such a data set, but we don't need to be so clever about figuring out the nature of this entanglement on its own. So here's one useful application of this approach. In this setting, the input image contains layout of the scene along with the material type at each region. Then the output image should be a photorealistic image that follows the input layout. Clearly, the input layout does not contain any pixels that look photorealistic. Therefore, it must be learned from the dataset during training. So here's our method for training such a model. Given an input image from the training set and the output of our model, we compare it with the ground truth photo and optimize our model to match that photo. On top of that, we're going to use the adversarial laws to enhance photorealism. We train our model on a large data set of paired examples. Given a photograph, we use human annotation to draw the layout of each photo. Our model is trained to the inverse operation, going from layout to photo. So let's look at the results of such approach. There is an existing works named Pixupix and its follow-up Pixupix HD that uses this formulation. So given these input layouts of the cityscapes dataset, we get these results. It produces quite realistic outputs. However, on more challenging dataset, we found that the results become quite bad compared to the real photographs. The new dataset contains more than 150 labels instead of just 20 labels of the cityscapes dataset. It seemed mysterious that the outputs don't achieve photorealism at all. So I began debugging this. As the simplest case, I created some toy layouts where all pixels belong to the same sky class. I pass it to the trained network of Pixupix HD, and I discovered that I actually get a gray image, which means I got zeros everywhere. Exactly same thing happened with another toy layout of grass label. I also get zeros. It almost looked like the model is ignoring the input and just outputting zeros. Why is this happening? After some investigation, I found that the issue was in the architecture of the network. A standard deep network consists of convolutional layers followed by normalization layers, which works by making each layer output zero mean and unit variance. We know normalization yields nice properties for image recognition, such as smoother gradient flow or invariance to input scaling. However, normalization causes too much invariance if the input is uniform. It's because the output of convolution is also uniform, and after normalization, everything just becomes zero. In other words, the input signal is completely lost in the middle of the network. So I started the fix by providing the input over and over after every normalization layer of the generator network. And by doing so, I could get the correct texture for the uniform layouts. I just got a message. 저희 목소리가 잘 안 들린다는 말을 들었는데 지금은 잘 들리시나요? 네, 계속 하겠습니다. So now let's take a closer look at how we provided the input signal. After normalization, we try to undo this harm by modulating the normalized activations by readjusting the mean and variance based on the input layout. The modulation is simply implemented by a few convolutional layers, and we named this module spatially adaptive denormalization, or SPADE in short. In the end, we could achieve much better realism than the previous method. So using this method called SPADE, we built a fun UI and presented it as SIGGRAPH. Basically, it looks like the Microsoft Paint app, but instead of the color palette, we provide semantic palette of material types like ocean, sky, rock, and sand. Our app generates photorealistic images with the appearance of photographs, but respecting the user-drawn layout. Lastly, note that there exist multiple plausible images that match the input. It would be nice if we can control the style of the output. So to do this, we added some stochasticity to the network by starting with a random vector sampled from Gaussian, similar to standard GANs. And on top of that, we additionally train an encoder network to capture the style of a reference image into the latent space. We also incorporated this feature into our UI. In the end, thanks to the paired supervision, our model achieves disentanglement of layout and appearance, along with the controllability of style, as well as high photorealism, like the reflection of the tree on the water. Now, let's take a step back and think about how useful this approach would be. Remember, training this model required preparing ground truth pairs at pixel level. What if we want to transform horses to zebras? We can collect a bunch of horse photos and also zebra photos, but we wouldn't be able to collect ground truth pairs of these images with a horse and zebra posing exactly same way on exactly same background. Well, we can still try throwing in the GAN loss, but the discriminator is going to be happy as long as the output looks like any zebra unrelated to the input. So because of this, in addition to the adversarial loss, we're gonna need another constraint. And to this end, we propose the cycle consistency constraint. We jointly train another image translation model in the reverse direction. And we enforce that the output zebra is back translated to the original horse. In more detail, given an input horse image, we first apply the forward mapping to translate into the zebra domain. Then we apply inverse mapping to reconstruct the input horse image. We simultaneously optimize the forward and backward mapping to minimize the reconstruction error. This can help solving the correspondence problem because for the correct translation, the back translation has small cycle loss, while for incorrect translations, the cycle loss is going to be large. This is the result of our method, Cyclogen. One advantage about Cyclogen is that it's relatively easy to train the model. And that's just because you just need to collect photos from two domains, and they do not have to be matching pairs. We can also apply Cyclogen to style transfer applications. Unlike previous single image style transfer methods, we learn the style from all of the artist's paintings. We are also kind of the first to do the opposite mapping, going from a painting to a photo. Cyclogen can also be used for data augmentation for autonomous driving applications like changing day to night. Here, we're translating individual frames separately so you can see the flickering of the night lights. We can also turn real driving scenes into the style of computer graphics. Especially, Cyclogen can be used for domain adaptation. So let's say the goal is to train a semantic segmentation model. The straightforward thing you can do would be maybe you can prepare a data set of these natural images, RGB images, and their ground truth segmentation maps, and train your segmentation model. Then you're gonna get 93% accuracy in doing so. But the cost of human annotation is going to be very high. And it's not even going to generalize to rare scenarios just because it's very hard to get a photo and labels for the rare scenarios. So you can try reducing the cost of training by training your model in computer graphics, where the segmentation can be auto-generated. However, because of the domain gap, the visual gap between CG and real, the accuracy drops considerably on real images from 93 to 54%. So to reduce this domain gap, you can train a segmentation model on the stylized images to match the target dataset using Cyclogen. This approach improves the accuracy to 83%, which was the state of the art at the time of study. Moreover, domain adaptation is not the only application of Cyclogen. It can be used in many different applications, ranging from object editing, font transfer, data generation of license plates, or even photo enhancement like image dehazing. It has been also used in other research fields like medical imaging, voice conversion, or even cracking simple ciphers. I think Cyclogen had an advantage of not requiring paired supervision with a loss function that can be generalized to other domains. However, it's not perfect at all. For one thing, 4 networks need to be trained, the 2 generators and the 2 discriminators in both directions, which makes it quite computationally heavy to use in conjunction with other models. Also, the cycle consistency loss is sometimes too constraining. And let me tell you in more detail what this actually means. Cycle loss is designed to promote sensible translation. By sensible, I mean the translated zebra should retain some resemblance to the horse image. To achieve this, an inverse translation function is learned at the same time to minimize pixel cycle loss. Of course, the back translation should be penalized if the pose becomes different. However, there are actually many plausible horses that may correspond to the same zebra. Once the horse is transformed into a zebra, the color information of the horse is lost. Therefore, it shouldn't really matter which color the back translated horse becomes. For example, a head of the horse should remain as a head, and feet should remain as feet as long as a head does not suddenly become a foot. This is all we need. So let's directly implement this idea as a loss function. First of all, we use a GAN discriminator to make the output look like a zebra, but we need to make sure that the structure is preserved. To do this, we consider a pair of input and output patch at the same location, and we enforce that the embeddings of these 2 pairs are similar. On the other hand, the patches from other locations should be mapped far from them. So we formulate this as a contrastive loss. The corresponding input and output patches form a positive pair. Patches from other locations are going to form negative pairs. In more detail, we use cosine similarities. We maximize the similarity of the positive pair while minimizing that of the negative pairs. We do this by formulating a classification task with the target class being the positive pair. This formulation, called InfoNCE, was introduced and used in several works in representation learning like MoCo and SimClear. However, unlike these self-supervised representation learning methods that used hand-designed data augmentation to produce positive pairs, we actually use outputs of the generator that's learned at the same time. To project these patches into the embedding space, we use the first half of the generator as our encoder. And we also found that computing the contrastive loss at multiple layers is important for stable training. In the end, our method replaces the fixed pixel-based cycle loss. And also, our method doesn't require a generator or discriminator in the inverse direction. And because of this, our method can actually be trained faster than Cyclogen with a smaller memory footprint. This may seem like a small thing, but it is actually going to be helpful when an image translation model is trained jointly with other models in a larger context. And this may include applications in domain adaptation, where a separate segmentation network is trained at the same time, or sim-to-real in robotics tests. And interestingly, we observed that the choice of negative patches is important. By default, we only sample the negatives from the same image, which we call internal patches. But at the same time, maybe we can include random patches from other images as additional negative images. And we're going to call this external patches. In representation learning, it's known that a large number of external negatives improve performance. Instead, here we work at the patch level, so we can actually use the same image as the source of our negatives. Indeed, when we tried to use external patches as negatives, the output quality was worse. And we hypothesized that it's because the output patches, or the external patches are too easy to distinguish, and they sometimes contain these false negatives like the highlighted horse head patch. In fact, the power of internal patches has been well known in classic texture synthesis work. More recently, training a super resolution network on the same but downsampled image was shown to achieve competitive performance to other methods trained on the entire dataset. And just like this, our model fully leverages the internal statistics of a single input image. Here's a visual comparison of using internal versus external patches. Compared to our default method, using the external patches causes more artifacts and signs of mode collapse. Also, we found that the samples from the target domain can be used for regularization following the identity loss used in Cyclogen. Normally, we compute the contrastive loss between the input horse image and output zebra image. But on top of that, we can provide a zebra image from the target domain as additional input to the generator network. And we still enforce the contrastive loss to prevent just making unnecessary changes to the input images. So in our final model named CUT, it's a short for contrastive unpaired translation, we use the identity regularization as well as the contrastive loss. As opposed to the pixel-based cycle loss, our loss is more flexible yet faster than Cyclogen. And just want to mention that our methods can be made even faster by not using the identity regularization, but just cranking up the weight on the contrastive loss. Here we show the training speed of our method compared to Cyclogen. Note that we use the same network and GAN loss. The only difference is the contrastive versus pixel-based cycle loss. Also, when compared to other methods, our speed is much better than the two-sided methods and on par with one-sided methods. Here are the visual examples of these baseline methods. So it can be seen that the CUT is able to make larger changes than Cyclogen. Just like if you look at this zebra texture that I highlighted, you can see that it is able to put larger zebra textures. Our method also performs well compared to the more recent models. And fast CUT, due to its larger contrastive loss, behaves more conservatively and hence more similar to Cyclogen. What do I exactly mean by more conservative transformation? Here's an interesting bias in the horse to zebra dataset. So I use an off-the-shelf semantic segmentation network, and I just counted the number of pixels that belong to either horse body or zebra body. And we found that the zebra pixels take up more than twice the horse pixels. And I think that's just a bias of the photographer. When photographers take picture of zebra photos, they tend to zoom in more to emphasize the stripe pattern. And in the end, what happens is the zebras in these photos tend to appear larger than the horse photos. Well, if we accept this as an existing underlying bias of the two data sets, should the output zebras of our model match the pixel frequency of the target or the source dataset? I think this is a very subjective thing, and it may be actually a matter of personal taste. In the more flexible cut model, we match the target zebra pixel frequency. So if you carefully observe this highlighted zebra, you see that the cut model actually enlarges the horse body. In the more conservative fast cut model, we better match the source, generating less zebra pixels. Still, both cut and fast cut make more changes than Cyclogen, which could lead to more artifacts in the background in doing so, like the artifact in the second row. But after all, just like Cyclogen, our default cut model or fast cut model can be used on various image-to-image translation datasets. One way to quantitatively evaluate the quality of the results is using FID. It shows that our method is more powerful in distribution matching. We also measure the segmentation score on the cityscapes dataset. We first train an unpaired image translation model from semantic layouts to photographs. Then we use a pre-trained segmentation network to predict the semantic class of each pixel. If the output images are realistic, the predicted segmentation should match the original layout. And we measure how much the prediction agrees with the input. The results show that cut can find ground truth correspondences better than the existing methods. Lastly, since our contrastive loss only uses internal patches from the same image, we can even apply our method on single image datasets. So here we take a high resolution painting of Monet and translate this image to the style of this target reference photograph using a patch discriminator. This setting connects image-to-image translation to image stylization method. So here's a famous painting by Monet. Using a reference photo, we apply stylization method first to turn the painting into a photograph. But you can see that it's actually quite difficult. Here's a stylization method by Gaddis. Here's another method called struts. And this is WCT squared from Neighbor. And you can see that all these methods are not really designed to do drastic changes that turn paintings into photographs. So the output photograph or supposed to be photograph are not very realistic looking. And this is our result. We also tried a patch version of Cyclogen with pixel-based cycle consistency loss, but you can see that it actually produces way more artifacts. Here's our result on Monet's water lilies. So let's checkpoint here, and let me summarize my works in the context of learning disentanglement. First, Spade was the easiest setting for learning disentanglement because the paired dataset directly suggested what the structure of the output should be. Next, we discussed the problem of unpaired translation, where we replaced paired supervision with domain supervision. We introduced the cycle constraint to separate style from the structure of the image. And then the next step is going to be taking one step further and discard this domain supervision as well. Within a collection of images, without any labels, not pixel labels, not image labels, can we still learn a meaningful disentanglement for image editing? This is my latest work presented at NeurIPS 2020. But before we moving on to this work, I think maybe this is a good time to take questions if there are any. I think there was one question on chat on Zoom. The input layouts for training is generated by segmentizing real images. Yes, so there are, so I think this question is referring to the Spade method. Let me go back. So Spade, just to recap, was designed to generate natural, realistic looking images from the layouts. And to train this, we need a paired supervision between the layout and the photo, right? And one way that we can prepare this data set is we first collect a data set of natural images, like this photo of person. And then we can actually have workers, have people to actually manually draw the boundaries and label the pixels of these input images. Then we're going to get these pairs of segmentation and its corresponding natural images. And we're actually training our model to perform the inverse operation, going from the segmentation to the natural image. If there are, oh, there's one more. And there's one more question. As for the loss of Cyclogen, do we need, sorry, here are some math. Maybe could you elaborate what your question's about? So he is asking in the formulation of Cyclogen. Oh, I think what he is asking is, so in Cyclogen, what we do is, just to recap, we translate horse to a zebra, and then this zebra back to horse. And our loss is that this back translated horse should match the input horse. And at the same time, Pyeongchang correctly pointed out that I was actually omitting the loss on the other side. So another loss that we can enforce during training is because we have this forward and backward generator networks, we can begin from the zebra image and then generate a realistic looking horse and then come back to zebra and enforce that this zebra is also back translated to the original zebra. And that is true. We're also using that loss. I was just not showing that loss in the slides just for the sake of simplicity. Thank you. Yep. So if that is all, let me resume. So now the goal, as I said before, is to go pretty much fully unsupervised. So we're going to have no supervision on pixels or no supervision on images and just learn some disentanglement that's going to be useful for image editing. So let's begin by contemplating what is the information that should remain unchanged after image translation. So these are translated images, and there is something that should not be changed between these images. I think it's actually pretty intuitive. A head should still be a head. And in other words, the structure is the representation that is invariant to changes in style across images. Sounds pretty obvious. On the other hand, style can be viewed as the information that stays invariant within the image, like this zebra stripe pattern, but they should be distinct between images. So we can maybe create this grid that shows the disentanglement of within image and cross-image variation. And it can be maybe compared to the content and style definition used by image translation models, including Munit, Drit, Funit, and also StarGAN. The similarity is that our method also does something similar to this content and style disentanglement, but the difference is that style, in their case, is defined by domain label supervision, just like my previous works. But in our case, we're trying to learn this disentanglement without any supervision. So let's directly model this definition of style in our image manipulation model. Given an input image, we want to stylize that using a reference image to produce some output. How can we check that the output actually captures the input style? Well, we can take random patches from this reference style image and test if an output patch looks indistinguishable. In this case, the output patch clearly stands out from the others, so the stylization was incorrect. But how about this case? In this case, the patches are indistinguishable, so the stylization can be thought as correct. So let me clarify what I exactly mean by style here. Style is a quite general and overused term. Our way of defining style is basically texture, and it goes back a little bit of history and is motivated by finding of Bela Illich, an experimental psychologist. He did many studies on how humans can distinguish texture. For example, in this image, you immediately see that there are two patterns. However, in this image, the distinction is not as clear, but magically, once we blur the pattern, it's easier to see different patterns existing in this sample image. After these series of these fascinating studies, he concludes that texture discriminator in human perception works by first extracting basic local features and then performing pairwise comparison of these features to tell if the patterns are the same. In other words, we should be able to set up a pairwise comparison test to see if the two patterns are the same texture. So let's do the test for ourselves. Let's take a data set of outdoor church images, and let's consider two random crops from these data set. Do they look like they are from the same image? The answer is no, it's not too hard to tell. What about these two? Yes, they are from the same image. And these two are from different images. But if we stylize this image, you see that it becomes much harder to answer. And we introduce a new adversarial training that exactly does this. So here's the full description of our method. First, our image manipulation model is modeled as an autoencoder, but unlike standard autoencoders, our encoder actually outputs two codes designed to represent structure and texture. And these two codes should have enough information to reconstruct the input image. Also, during training, we randomly sample another image from the dataset, extract their codes, and perform swapping of the codes to produce a hybrid image. So this is where swapping comes into play. Then we take a random crop from the hybrid image and compare it to the random crops of the input image. We train a patch-based co-occurrence discriminator that tells if the patches are all co-occurring from the same image. In conclusion, our method learns the disentanglement of structure and texture. And note that this style and or texture and structure grid may look similar to the style content swapping grid of the StyleGAN paper, but it's actually very different in that the input images are existing real images. And I think you can recognize some of the images here, like Notre Dame Church in Paris and Sagrada Familia in Barcelona. And embedding these images into the latent space of StyleGAN is actually a very hard, non-trivial problem. And we don't suffer from that problem. And this is the result on the Elson bedroom dataset. And you can see that the unique pattern of the style images are transferred. Because our method is an autoencoder, embedding input images, as I said before, is just one feed-forward pass of the encoder network. And the reconstructed images are accurate because our structure code still retains the spatial resolution of the input image. And here are the results of using standard unconditional GAN-based approaches using test time optimization. You can see that the reconstruction quality is worse, and they are also too slow for interactive image editing. Our quality of swapping is also better than the existing method. The standard GAN-based methods produce unrealistic images, and we also compare our methods to style transfer methods, and they don't look as good as ours. But what's more interesting about our method is that embedding space turns out to be smooth, allowing vector arithmetics. So if we collect 10 images of summer mountain that shows up on Google search, and we encode the images and average the codes, we get the code that represent summer mountains. We can do the same thing on snowy mountains. And if we take the difference of these two vectors, we're going to get a manipulation vector that will add snow to the other images. So these are user-provided test images like Yosemite in California. We add this snow vector from previous slide, and you can see that it actually adds snow to these input images gradually. And subtracting this vector actually removes snow. If collecting these 10 images on Google search is too much of a hassle, we can actually just run PCA on the codes of the training set, similar to the idea of GAN space. We found that the first principal components are all meaningful edit vectors. Our method can perform smooth interpolation of high-resolution images. It can change weather condition, vegetation, season, color saturation, and many other things. Moreover, we built an interactive UI that lets you upload your own photos and begin editing. On the right side, you see previews of manipulating with the first 10 principal components in either positive or negative directions. You can see that they are all reasonable edits. Furthermore, now that we have disentanglement of structure and style, we can separately edit the structure of the image while maintaining the style of the image. For example, you can change this mountain line, mountain ridge line between sky and mountain, or change the river to make it a full circle. And these are the results of directly editing the structure code by simply cloning the code from other parts of the image. Our method can also do domain translation if we just combine different domains as one large data set. And domain translation just boils down to finding some meaningful manipulation direction in the latent space of swapping autoencoder. Using the UI, the user can control the output style. This often results in superior quality. On faces, because the facial landmarks are already aligned in the dataset, we can kind of do this hack by running PCA on the flattened structure code to enable spatial editing. I like landscape photos, and I'm just very happy to see that my model can perform new types of image editing. I also wanted to share my thoughts about what can be done as a next step. Because our model is not required to learn about the underlying 3D structure of the scene, our model tends to make modifications to the structure. So you see here that the tree leaves are growing and shrinking, and it's because there's correlation between astrophotos and the amount of sky. So what I'm saying is that if it's a star photography, photographers tend to show more sky by pointing their camera upward. So our model reduces the size of ground, and that's just the correlation that's discovered by our model. But because of this, the underlying scene structure ends up changing, and maybe this is not what you want as a person who wants to edit the original image. One way to prevent this is to utilize some knowledge about 3D or physics. We can have our encoder also output some physics-based representation and enforce that the representation is consistent after some modification, like viewpoint changes. Then the encoder is almost like the whole 3D computer vision problem, maybe. On the other hand, the decoder is like a computer graphics pipeline. So it surely sounds like a very difficult problem, but there are interesting feature representations that seem useful for my purpose. So there's Hologen and NERF and many follow-ups of NERF paper. But also 2.5D representations like depth map or NPI are going to be enough for my purpose because I don't actually need perfect reconstruction of the scene in all angles. We're only interested in some intermediate representation that produces plausible images to human eyes under some small manipulation. In this sense, I think some variations of 2.5D representation is going to be suitable for this purpose. Thank you for listening to my talk. If you have questions or comments, I'll be happy to answer.